whether you say M12 or M21, they're going to be equal. It is just mutual inductance of the pair of coils. So that is the mutual inductance of a solenoid with a secondary winding. Let's look at the last equation again. N1 is the number of turns on the solenoid. N2 is the number of turns in the secondary winding. A is the area of cross section of the solenoid. In fact, if the secondary winding is done over the solenoid, don't you think that their areas will almost be the same? Yeah, so that's usually the case. And let me ask you this. Does the mutual inductance depend on the current flowing?
Yes.
Does the mutual inductance depend on the current flowing? The answer is no, because this formula does not have current in it. The mutual inductance depends on the geometry of the coils. As you can see, the number of turns in both of them, the area of cross-section, and the length. So how can you have a higher mutual inductance? By having a larger number of turns on both, by having a bigger area of cross-section and a smaller length. That means having turns as close to each other as possible. And of course, using a ferromagnetic material like iron, which will further increase the mutual induction between the coils. Okay. Trying to get a formula for self-inductance of a solenoid. Two coils, coil 1, coil 2, there is a current flowing through coil 1, which is I1. And definitely you see the magnetic field, blue arrows. There is going to be a magnetic field associated with coil 2, and therefore there's going to be an induced EMF in coil 2. Did you notice that? So because of a current flowing through coil 1, there is an induced EMF in coil 2. This is called mutual induction. And I'm going to write phi 2,1, and you have to read it as the flux in 2 due to the current in 1. The flux in 2 due to the current in 1. And to get the total flux, of course, you have to multiply with the total number of turns in 2. Correct? Therefore, the total flux N2 phi 2,1 will be equal to, I'm saying that's the total flux in which coil? In the second one. And according to the formula that I just told you, we can write this as a constant multiplied by I1. Let's stop right there and think. Now that constant is mutual inductance, not self-inductance. And it's written like that to show that it's the mutual inductance of 2 with respect to 1. Is that equation making sense? The flux, total flux associated with coil 2 is equal to mutual inductance multiplied by the current in coil 1. That is an important equation. But using Faraday's law of electromagnetic induction, when you differentiate, you're going to get M21 dI1 by dt, because E is minus d phi by dt, isn't it? Same thing. It's called the mutual inductance of coil 2 with respect to coil 1. Now let's think in the other way. What if there was a current flowing through I2? Wouldn't there be a flux associated with coil 1? There would be, right? And the thing is, the mutual inductance of this pair is a constant. So whether you say M12, the total flux is on the left side, N times phi B. So what is phi B? Phi B is the flux linked with one turn, isn't it? So when you multiply it with N, you get the total flux linked. Isn't it equal to Li? Please don't let it be a mad rush of writing notes without understanding. So N phi B is Li. Make L the subject. You will get N phi, simple math, by the length. And what is phi? Isn't phi B times A? Okay? So we're going to use this formula to find the inductance of a solenoid now. Just continuing from there. Phi is B times A. So you have B times A by I. Okay. And what is B? For a solenoid, what is B? Mu naught Ni by the length, isn't it? For a solenoid. Come on now. Let me stop there. Isn't B for a solenoid mu naught N times I by the length? Okay, we got that. So that's simple substitution. And therefore, that makes it mu naught. See, I had forgotten to divide by an I there, so, which I did now. So that's the formula for self-inductance of a solenoid. Of course, N is the number of turns, total number of turns, A is the area of cross-section, and L is the length. Once again, how do you increase the self-inductance of the solenoid? What's the most important term? Definitely the most important term is the number of turns because it's squared, isn't it? So try to have as many turns as possible on the smallest length. That's the important thing, and try to have a big area of cross-section. So I'm repeating this as a summary. We're trying to find the work required to take the current from 0 to I. Work is P dt. Power is the product of current and EMF. So EI dt. But induced EMF is L di by dt. Just the magnitude without taking the sign, right? Substitute. So now work is integral 0 to the maximum, if I or I naught, Li di, which gives half Li squared. So remember the symbol for energy is U. Haven't we been using that? Potential energy, U. 1/2 Li squared. Just remember, L is the inductance and I is the maximum current. So you may want to write it as I naught, just to show that it is the maximum current. Ooh, that's a big one. An inductance and a capacitance together. Let's try to combine an inductor and a capacitor together. Let's see what happens. But you have to, this is one.